Recording
Okay.
started.
Okay, so the recording has started, so just so you know, this is being recorded. And again, if you have a question, please type it in the chat box, and I'll be able to, I will look at that periodically to see what questions there might be. This webinar is on sets, and it's for MAT 115. Some of you may be studying sets this week. Some of you may be studying sets next week, but we wanted to include the webinar this week so that it catches different people on different schedules. This way, all of the 115 students would have an opportunity to see it either during or before they are studying sets. So just wanted to make that clarification. What we're going to be looking at is to understand and use some definitions and symbols and operations of sets. So we'll be looking at some basics with sets to give you a good foundation for starting the chapter on sets. And then we're also going to look at some Venn diagrams, because this is a really good visual for illustrating how sets are related and how they interact with each other. So we'll be doing those two things in this webinar. First of all, I'd like to start off with defining a set, that it's a collection of objects, which sounds basically just like a basket of things. And so it's not a real fancy definition. It's just if you think of a set as a basket, and the objects in the set are just things placed in the basket. And it doesn't matter how they're arranged in the basket. They're just in the basket. If they're in the basket, they're part of the set. If they're not in the basket, they're not part of the set. And the objects in the set are called elements or members. Those two words are used interchangeably throughout the information that we'll be looking at with sets. So elements or members are the objects that are in the set. Think of that as whatever items are in the basket. So let's say we have a set with the numbers 1, 2, 3, 5, 7, 9, and so on. Notice I have a ... after the 9 to show that this list goes on and on and on forever. It's the odd numbers. And so we actually have 3 different ways to write what that set is. There's a description. So one way would be a description, and that's where we just write out, it's the set of all odd counting numbers. Counting numbers are the numbers you use to count. So when you're counting like people in a room, you start with 1, then you go to 2, and then 3. So those are counting numbers, and it's only the odd ones in this set. So that's our description. Another way is to write a list. And notice in the list we have curly braces. So we start off with a curly brace and then 1, comma, 3, comma, and in between the elements of the set you put a comma, and then when you get to the end you put a curly brace. And in this case the end is the ... because it goes on forever. So after the ... we put the closed curly brace, and that's another way we can write a set. The third way is called set builder notation, and that is where we have the curly braces, but it's basically taking the description and including it with a variable. This vertical line that you see there is not any kind of mathematical computation. It's just like a separation line. And so to the left of the line is the variable. That's where you write whatever variable it is that you're working with. And then to the right of the line, you're describing the values for that variable. So in this case, X is an odd counting number, which looks a lot like the first one we have here with the description. It's just now we're using a variable and saying we have a variable X, and then what values can we have for X? On the other side of the vertical line, it tells us X is an odd counting number. And how you read that from left to right would be X such that X is an odd counting number. So that vertical line is actually pronounced such that. Not that you'd have to pronounce it, but just so you know, it's not any kind of mathematical computation, but it is a way that we have to describe a set. So there's 3 different ways that we can list or describe how what the elements are in a set. We use a capital letter to name a set. So, for example, we could call the set that we have as set A, to just pick a letter. And so we would say A equals, and then after the equal sign, put what the set is. In this case, I'm using the list notation with the curly braces and just writing a list. And then we have the symbol for element. It looks like a kind of rounded E. That is the symbol for element. So we could say that 1 is an element of A right there, because if we look at set A, the number 1 is included. So we could say 1 is an element of A. Notice here I have an element with a line through it, like the element symbol, but with a line through it, meaning not an element. So that symbol with the rounded E with a line through it, that means it's not an element. So we could say 2 is not an element of A, because if we look at A, 2 is not included. So that's some other symbols, basic symbols that we work with sets. Also, set A we call an infinite set, because the number of elements cannot be counted. So because of the dot, 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 that, and then it ends with the dot, 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 meaning that it just keeps going and going and going. And because of that, we call it infinite. We cannot count the number of elements in that set because it's an infinite set. Now I'm going to define a set U. Let's say that U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll call this the universal set. A lot of times we use U for the universal set. And a universal set is a special set, and we normally use U to represent it because U, universal. It's a special set because it lists all of the elements in a particular situation. So if you're working on a certain problem, in the directions you might see U equals, and it'll define what is in the universal set. And basically that's telling us this is what we have to work with in this situation. So in this situation, I have U as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I also define a set B as 1, 3, 5, 7, 9. Notice that these are two sets that actually do not go on forever and ever. Sometimes you have sets that do, like we did with set A, but in this case, we have sets U and B that we call finite because they don't go on forever. We can count the number of elements in each of these sets. So set B, for instance, I count, it has 5 elements. So we say this N parentheses B equals 5. That is the notation for showing how many elements are in set B. N standing for number of. So it'd be like number of elements in B is 5. So the little N in the front is what that means. So if you see that notation, that's what they're talking about, where you're counting how many elements are in the set, and you can do that because it's finite. If you see a B with an apostrophe or any of these capital letters with an apostrophe, it means all of the elements that are not in that set, but are in U. So because they're part of the situation, meaning these are the numbers, in this case, numbers 1 through 10, those are the numbers we're working with, but which ones are not in B? And that little apostrophe means the complement. So we're taking the complement of B, which is everything not in B. Sometimes you might hear me refer to it as B prime. That little apostrophe we call it as prime. So we have B and then we have B prime, and B prime is the complement of B. And notice I've listed for B prime all of the numbers that are in U that are not in B, because B was 1, 3, 5, 7, 9. So B prime, which is the complement of B, would be the 2, 4, 6, 8, 10. And I've listed a few things here to practice again, just using the element symbol, that 1 is an element of B and 2 is an element of the complement of B. And whenever you're looking at stuff like this, it's nice to have written out, you know, the listing. So for B, complement of B, we have 2, 4, 6, 8, 10. So it's very easy to see that that's true, that 2 is an element of B prime. And I can say that 3 is an element of U here, because when I look in set U, I see a 3. And then notice this one does have a line through it. It's not as dark as I think as the other lines, but it is saying 2 is not an element of B. It has a slash through the element symbol. Because remember, B is 1, 3, 5, 7, 9. Okay. Some questions to consider. Is set U infinite or finite? And I listed set U there. And the correct answer is finite, because the infinite sets are the ones we cannot count. I can count how many elements are in U. In fact, I wrote it down here. The number of elements in U is 10, because I have 10 numbers there. So I could do a little n with the U in parentheses is equal to 10. How many elements are in the complement of B? Well, when you count the number of elements in the complement of B, you get 5. So the number of elements in the complement of B would be 5. And it's very useful. Notice that for both of these, I wrote right next to the problem, this is U, this is the complement of B. It's a whole lot easier to answer these things when you have the set written out right there as you're trying to answer it. So for instance, if the problem just had U written out and B written out, but didn't have the complement of B written out, in order to answer this one, the first thing I would do is write out the complement of B, then answer the question about the complement of B. Don't try to think of the complement of B in your head. There's no extra points for doing it in your head, and it's a lot easier to make a mistake that way. So it really helps to look at the set if you're answering a question about a set, to write it out. So I'm answering a question about the complement of B. I'm going to write out the complement of B so that I can count how many elements and see that it's 5. Okay, so that's some definitions and some symbols related to sets as an introduction. Now, what I'd like to do is talk about some Venn diagrams and how this relates to Venn diagrams. When we draw the universal set, it's a rectangle. And then the other sets are circles. The universal set is different than any other set, so we make it look different by drawing it as a rectangle. And then all of the other sets would be inside the rectangle. So I drew a circle to represent set B. There's my B there for the circle. And so I'm able to see that inside the circle are the numbers 1, 3, 5, 7, 9. And inside the universe, though, I also have 2, 4, 6, 8, and 10. Notice that all the numbers 1 through 10 are inside the universal set. They're inside the box. But the particular numbers that are part of set B are inside circle B. And notice also that when I drew the numbers, I kind of haphazardly put them in there. They're not in a particular order. They don't have to be placed in certain areas around each other, because as long as they're in the basket, that's all that matters. They can be mixed up, and as long as this numbers 1, 3, 5, 7, and 9 are inside circle B, that's really all that matters for that. So some other definitions, and as we're working to take a look at this picture again, if we take a look at circle B, all of the elements in B, set B, are also in U. So those have a special relationship. We say that set B is a subset of U, and the subset symbol looks like C with an underline under it, okay? And that just means that all the elements in, if we say that B is a subset of U, that means all the elements in B are also in U. And if we take a look back at the Venn diagram, we can see all the elements of B are also in U. We can also look at that with the listing. Let me go back to the listing here. That here's my elements of B, and all of those numbers are also elements of U. All of those, 1, 3, 5, 7, 9, are all in U as well. Okay, so we can say it qualifies as a subset. Now, notice that the complement of B, that's the 2, 4, 6, 8, 10, those are also in U, so we can say that the complement of B is also a subset of U. There are other subsets of U. We can say that 1, 2, 3 is a subset of U, 4, 2, 4, 5, 6, 8 is a subset of U. Basically, what qualifies it as a subset is that all of the elements in that set have to be in whatever's on the right. In this case, on the right, we have a U. So 1, 2, 3, those are all elements of U, so that counts as a subset. 2, 4, 5, 6, 8, those are all elements of U, so that counts as a subset. We can also do subsets of B. Set B is 1, 3, 5, 7, 9. So I see 1, 5, the subset 1, 5, that's a subset of B if I just take the elements of 1, 5. Notice with this one, it's kind of a special case here. I have the set 1, 3, 5, 7, 9, and I say that is also a subset of B. Remember, B is 1, 3, 5, 7, 9. So it is a subset because it fits the definition that all of these elements are also in B. So and that's going to happen with every set. So we can say that every set is a subset of itself because it fits the definition that all of the elements on the left side are also on the right side. So U is a subset of U. Complement of B is a subset of a complement of B. We can do that for all of the, every set can be written that way. We have a special set, another special set called the empty set. And the empty set it's just like what it sounds like. It's a basket with no elements. So you have a basket and there's nothing inside. So there's a couple of ways you can notate that. One way is with that symbol there where it's a circle with a slash through it. That's one way to notate an empty set. Another way would be the curly braces with absolutely nothing in between them. That shows that it's empty. So the circle with the slash through it is the same exact thing as the empty set. And we can say that the empty set is also a subset of B because it does meet the definition. If we look at the empty set and subset of B, B is 1, 3, 5, 7, 9. When I take a look at that, my empty set, there's nothing over there that I can say is not part of B. Everything in the empty set, everything in here is over here. Of course, it's nothing, but there's no way for me to say, oh, well, it's not a subset because of this element. I don't have that. There isn't anything for me to say that with. So this is a subset. The empty set is a subset of every set, including itself, because you can still, because every set is a subset of itself. So I can say the empty set is a subset of the empty set is a subset of U. All of those are true for subset. So the empty set is a special set that has nothing in it. It's basically a basket with nothing in it. So let's look at another example just to get another idea of subset. Let's consider the set G that just has the letters A and B in it. What are all of the subsets of G? We list them all the possible subsets of G. Well, there's the empty set, there's the set that just has an A in it, there's the set that just has a B in it, and then there's the set of A and B, because that also qualifies as subset. So all of these four are true statements. There are actually four subsets of set G. Okay. If we made the qualification that we could only look at ones that were not equal, because this is equal. So I say A, B equals G, okay? But if I made the qualification that a subset could not be equal to the set, then I'd have to eliminate this one if I made that special clarification. And actually, there is a time that happens, and we call that a proper subset. A proper subset is like a subset but slightly different because we are taking out the one where they're equal. So it has to be a subset, but does not contain all of the elements of the set. So you can't have a proper subset of itself. So let's go back to this, okay? This is listing all of the subsets of G. For it to be a proper subset, it has to be a set, but it cannot be equal. So that would be like this. And the proper subset symbol is the C without the line under it. So we have empty set, we have A, and we have B. And that's it. For proper subsets, it's the empty set, A, and B. The subsets include all four of these. The proper subset, you have one less because you have to eliminate the one that it's equal. The AB is equal to G. We have to eliminate that one. So a proper subset, where it's because all the elements of B are also in U, B does not contain all the elements of U. So a set cannot be a proper subset of itself because a proper subset cannot contain all of the elements. So if we look back here, in this case, G is a subset of itself. But over with the proper subset, G cannot be a proper subset of itself because I've eliminated the possibility where they're equal. Okay, so a set cannot be a proper subset of itself because if it's a subset of itself, then the elements are equal. That doesn't work with proper subset. Okay, so let's take a look at the symbol of proper subset, and that's, like I said, the line without the C without the line. So if you think of the line underneath it as being the equals, like this symbol here has that line, like it has a C with a line under it. If you think of the line under it as being equals, then it kind of makes sense that these are allowed to be subsets but not equal. So B is a proper subset of U, because remember B is 1, 3, 5, 7, 9, and U is 1 through 10. The complement of B is a proper subset of U because the complement of B, that's 2, 4, 6, 8, 10, and U is 1 through 10. This is a not proper subset. 1, 3, 5, 7, 9 is not a proper subset of B because they're equal. The empty set is a proper subset of B because B is 1, 3, 5, 7, 9. So we're good there. And then another proper subset of B would just be a 1. Another proper subset of U would be a 2, 3, 4 set. So these are just a few of the statements that we can make with the proper subset symbol. Of course, there are other proper subsets of B and U. Now, the empty set is a proper subset of every set except itself, because if I have this, that's a problem, because in this case, they're actually equal, but there is no equals part to the proper subset symbol, so we can't have that, okay? But the empty set can be a proper subset of every other set, as long as it's not, just not of itself, okay? And then just this reiterating about subset, the empty set is a subset of every set, including itself. So that's just something to be aware of, especially as you're answering questions, going through assignments, that you can have the empty set as a proper subset of every other set except itself, and the empty set can be a subset of every set, including itself, because with subset, they can be equal. So let's take a look at set G again that just has A and B in it. The proper subsets are all of the ones we listed before, just without the one that has A and B. A and B is missing from the list because that's where they would be equal. Let's take a look at a Venn diagram with two sets now. Let's say I still have my universal set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. B is still 1, 3, 5, 7, 9, and I'm going to introduce set D, that's 1, 2, 3, 4. Now notice the universal set is still a box. You'll have this box. And then the sets on the inside of the universal set are circles, and I have them labeled. Here's set B and set D. And notice that inside of set B, inside circle B, I have the numbers 1, 3, 5, 7, 9. So again, just like the other Venn diagram I drew, they don't have to be, because they're kind of floating around in the basket B. And notice in circle D, I have 1, 2, 3, 4. And in my universe, I do have the numbers 6 and 8, which are not in B or D. So I had to put them out here. They're in the universal set. They're just not in one of the circles, okay, because they're not in B or D. Notice also I have my two circles overlapping, and in the overlap, I've put the numbers 1 and 3. And that's because if you notice, numbers 1 and 3 are in both sets. There's set B and set D. There's set B with 1 and 3, and set D also has 1 and 3. And so they are overlapping. And something else I'd like to mention, which I don't think I've mentioned so far, is that when you're listing the sets like U, B, or D, you don't have to put them in numerical order. I'm putting them in numerical order just because it's easier to look at. But if I wrote set D as 1, 3, 2, 4, it would be the exact same set. It would be exactly the same. So it's just a listing. It's just items thrown in a basket. They don't have to be in numerical order, but I'm doing that just because it's easier to look at. But okay, so I have 1 and 3 where the two circles overlap because 1 and 3 are in both sets. And notice over here I have 2 and 4 that are in circle D but are not in set B. So they're over here in this part of circle D so that they're not inside set B. That's on purpose. And then these 5, 7, 9 numbers are in set B but not in set D. So I have to purposely put them so that they are not inside circle D. So it doesn't matter where in the region they are, but they do need to be in the correct region. Okay, so what I wrote next is just the circle on the left is set B, circle on the right is set D, and you have to put the elements in the circle where they intersect. 1 and 3 are in the regions where they intersect. And if you're frantically writing, you don't have to frantically write all this down because I can email you my notes. So I'll give you my email address at the end so you don't feel like you have to write everything down. And even if you're listening to the recording, just send me an email. The email address is at the end, and I can email you these notes so you don't have to write it all down. Okay, so let's take a look at the intersection of the two sets. And I know I've talked about this already a little bit because B and D have the numbers 1 and 3 in common, and that is why they are in the region that I've colored in pink. And I wanted to point this out because actually intersection is a vocabulary word dealing with sets. It's where the circles overlap. It's where the sets overlap. Think of overlap. That's key. Oops. Help us spell overlap. That's key for intersection. You want to see the overlap. So that where 1 and 3 are in that region, that's where B and D overlap. And then this is the symbol notation for it. Notice that in between the letters B and D, I have like a upside down U. And that upside down U is the symbol for intersection. And so I could say B and then the intersection symbol, and then D equals the set 1, 3. So we can see it in the diagram that it's 1, 3, and then we can also look at the listing of set B and set D and see that they both have a 1 and a 3. Now let's say we're going to put sets B and D together. Like we take the two baskets and we dump them together. And if we dump them together, then we would have 1, 2, 3, 4, 5, 7, 9. If we take both of those and dump them together. And so of the two sets,
recording started.
Where that's called the, hold on a second. It's still recording. Sorry, I just got a message that recording started. The union of the two sets would be where you take the two sets, dump them together, and that new set that's formed is called the union. You're just combining the two sets together. Okay? So that would be in our diagram, that would be shading in all of circle B and all of circle D together. That makes one set, that's like one basket, and the symbol for union is the letter U. So it looks like bud, I know, but it's not bud. It's set B and set D, and the U stands for union. That's the symbol for union, and that means that you put the two sets together to make one big set. So that would be 1, 2, 3, 4, 5, 7, 9. And again, the listing could be in a different order. You don't have to put them in numerical order. If you wanted to write this as 2, 3, 1, 4, 5, 9, 7, it's the exact same thing, okay? It doesn't have to be in numerical order. All right, so the Venn diagrams we've been looking at, I already had the numbers filled in. So I'd like us to do one where we're going to fill it in together. And like I said, I can always send you an email, a copy of these notes if you want. But we're going to fill in the sets. And I wanted to do this one in particular because I have 3 sets in the situation. Because sometimes you have 1, sometimes you have 2, sometimes you have 3. You can go more than 3, but really in your homework, you're just going to go up to 3. So we'll stop with the 3. But I've created another set H, which just has 1 and 5. So we're going to fill in the numbers where they go. And the key is where you want to start with this is where all 3 circles overlap. That's a really good starting place when you have multiple circles. And this piece right here, that piece right there, I don't know if you can see that. Let me make it darker. That is where all 3 circles are overlapping, and that is where we're going to start, okay? So we're going to look at sets B, D, and H to see what I should put there, which would be a number that's common to all three. And if I look at B, D, and H, I see there's the number 1 that is common to all three. So I'm going to put a number 1 right there where the 3 intersect. Now I'm going to take a look at B and H. Well, no, we'll do B and D. When I look at sets B and D for a minute, I already wrote the 1. Is there anything else they share? Well, they share a 3. So I need to put the 3. Now where the 3 is going to go, it's not going to go in the same region I put the 1, because the region that the 1 in is what's common to all 3 circles. But now I'm writing what's common to just B and D, and that would be that spot right there, where B and D are overlapping, but it's still not in circle H. It's outside of circle H. Okay, so now let's look at B and H. So we have 1 written, we have 3 written. Let's look at B and H. Notice they share a 5. So I need to put a 5 in my diagram where B and H overlap. That is not in circle D because there is no 5 in set D. So I'm going to put a 5 right there where B and H overlap outside of D. And let's see here. Set B, notice now if you look inside circle B, I have 3 numbers. I have 1, 3, and 5. But set B has 1, 3, 5, 7, 9. So the 7, 9 need to go inside circle B, but not in any of the other circles, because 7 and 9 are not in any of the other circles. So I'm going to put 7 and 9 in that spot, in that region, inside B, but not inside any of the other circles. And then let's see what other numbers. D, I have 1, 2, 3, 4. If you look inside circle D, I just have a 1 and a 3. Now, D and H don't share any numbers besides 1. But in D, I do have a 2, 3, 4. I already wrote the 3. So I need to put the 2 and the 4 inside circle D, but outside of the other circles. Now, circle H, I'm good, because circle H has 1 and 5. If I look in circle H, I have a 1 and 5. But there's still numbers I'm missing, because if you take a look at the diagram, we have 1, 2, 3, 4, 5, 7, 9. But what about 6, 8, and 10? Well, 6, 8, and 10 are still in the universal sets, but they're not in B, D, or H. So I need to just draw those out in the universal set, but not inside a circle. And again, I didn't have to put them here. I could have put 10 over here, you know, as long as it's inside the universal set, but not in a circle. So that's filling it in. Notice what I did is I started in the inside where all 3 circles overlap, and then I worked my way out of the diagram. So when you see a 3-circle diagram, it's a good place to start is in the intersection of all 3 circles. Okay. All right. I know I need to fill in the numbers here. 1, 3, 2, 4. Real quick. Okay. That was missing numbers. So I have the numbers in the diagram. It's the same diagram. Let's take a look at the union of sets with this picture. So I know it looks like hub. It's not hub. It's set H, which is the circle H, and then a union with circle B. So what that's doing is we're taking set H and we're taking set B, and we're throwing them together in the same basket, which would look like, if I colored in, would look like this here. That is H and B. So the region that I have shaded, let's take a look at what would be in that set. Well, that would be 1, 3, 5, 7, 9. That's in the HU union B. Now, notice the next one. I don't want the parentheses to scare you. What that means is, parentheses means just do what's inside first, and then find the complement of it. Well, we've already done what's inside. That's what we just did, 1, 3, 5, 7, 9. So the complement would be all the other numbers. That would be 2, 4, 6, 8, and 10. That would be the complement. Okay? You write these, erase the shading there. Let's move on to the next one. D union with the complement of B. So that's telling me I'm going to shade circle D, union meaning I'm putting it all together. So circle D is part of my answer, as well as what's outside of circle B. Outside of circle B is all of this. It does help when you're doing these problems to draw the Venn diagram, label it like I have, and then just start shading. It does help to see what the answer is. Okay, so I've shaded everything outside of circle B and everything inside circle D. And I can see what I'm left with. That's 1, 2, 3, 4, 6, 8, and 10. Okay, so after I have shaded it, I can look in the picture to see what should be part of that answer. And then for the last one, let me go ahead and, when I erase the shading, I erase the numbers. For the last one, we are going to shade everything outside of circle D and outside of circle H. So let's do that. Outside of circle D is all of this. Outside circle D. And then outside of circle H would be this piece here as well. That's outside circle H. So I have all of that shaded. Notice there's only one little piece that's not shaded. Okay, so my answer would be all of the numbers except 1. You see, 1 is the only thing not shaded. So it would be 2, 3, 4, 5, 6, 7, 8, 9, 10. Like that. Okay? So that's some examples dealing with the union, and that's where you're taking two sets and you just dump them together. The next example deals with the intersection, where we're looking at, we're going to do some problems with intersection of two sets. Remember, with intersection, that's the upside down U, and that's where you're looking at overlap. So this first problem is asking us to look at the overlap between B and H. The overlap would be this piece right here. And notice that we do have two numbers in the overlap, so the answer for that one would be 1 and 5. The overlap between B and H. Okay, the next one is asking us for the overlap between B and the complement of D. So the complement of D is everything outside of circle D. And so what I'm going to do is I'm going to shade two different colors. I'll do everything outside of circle D in gray, just to help illustrate. Because remember, the overlap is the answer when you're looking at the intersection. So everything outside of circle D. And then I'll do the inside of circle B in green. So there's that. So you can see where the gray and the green overlap. that is the answer for the intersection between B and the complement of D. And if you notice, that's three numbers, 5, 7, and 9, are where the intersection of B and the complement of D. You can see how the shading really helps with illustrating things like complement. Okay. The next one is the complement of the intersection of B and D. And we already did H and D. We did not do the intersection of H and D. So we're going to shade circle H and shade circle D, see where they overlap, and then take the complement of that. So circle H, I'm going to shade that in gray. And then circle D, I'm going to shade that in green. So you can see the overlap of the shading is 1, and that's it. The only number that is common to both, the intersection of H and D, is 1. So the complement of that is everything except 1. So that would be everything except 1. So that would be 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, for the intersection of H and D, all you have is 1, so then you take the complement, meaning everything except 1. Okay. And the last intersection problem I have here is the complement of B intersecting the complement of D. Okay, so the complement of B, I'll shade that gray, and shading different colors when you're trying to find the complement really comes in handy because it's easier to see the overlap when there are two different colors. So you could use different highlighters. Some people use pencil and pen, like color one in pencil and color one in pen to try to see where they overlap. Highlighters work good too because they're really see-through. You can still see the writing. Okay, so I did complement of B in gray. I'll do complement of D in green again. So I'm going to complement of D, so I'm shading everything outside of circle B. Shading all of that. Outside of circle D is green. Okay, so let's take a look at where the green and the gray overlap. It looks like the numbers 6, 8, and 10. The numbers 6, 8, and 10 are where green and gray overlap because 2 and 4 are just in gray, 1 and 3 are in white, 5, 7, and 9 are just in green. So I'm looking at 6, 8, and 10 as the answer to that one, where they intersect. Okay. And I know we're running out of time a little bit, so we're just going to finish. I'd like to finish up with a true or false listing. We can look at these to see whether they're true or false, because when you're doing these set problems, they like to throw true-false at you. There's a lot of that happens. So let's just practice a couple true-false, trying to get used to the symbols. Notice the first one is the element symbol that we talked about at the beginning, where we see 3 is an element of the 1, 3, 5, 7. So this one would be true. The next one, 17 is an element of 1, 2, 3, 16. I'd like to point out that this ... does not mean it's an infinite set. The other one where the ... was at the end, that meant it went on forever and ever and ever. But this ... is in between the numbers 3 and 16. So it doesn't mean it goes on forever. It means it's just filling in the space between 3 and 16 to save space. So it's not an infinite set. This one does end at 16. So this would be false. That 17 is not part of that set. Let's take a look at the next one. 7 is not an element of 7, 8. At first glance, you may say, oh, that's false because 7 is in 5, 7, 8. But notice that 7 is in curly braces, which means it's not an element, it's a set. When you put it in curly braces, you're saying it's a basket. That curly braces, think of it as a basket. So I have a basket with 7 in it, and they want to know, is that an element of 7, 8? And it is not an element of 7, 8 because 7 is an element of 7, 8, but not the set 7. So it's not exactly the same. So this is actually true, that is not an element of 7, 8 because of the curly braces. When you look in the set 7, 8, the 7 does not have curly braces around it by itself. So you don't have that as being an element. The next one, number, the little n in the front means number of. So if you have this set that is months of the year, the number of months of the year is 12, so that's true. That's just an example dealing with the number n and the letter n in the front, where you're taking and counting the elements. The next one, the empty set symbol is what they're saying there. That empty set symbol, they want to know, is it an element of the empty set? And that is false, because the empty set is empty. There's nothing in the empty set. The next one, you have Mercury, Venus, Earth. Venus, Earth, Jupiter. Is that a subset? That is not a subset. That's false. Because of Mercury. Mercury is not part of the Venus, Earth, Jupiter, which is on the right side of the subset symbol. So that one's false. This is true because it's saying the subset is the empty set is a proper subset of 2, 4, 6. This is also true because the empty set cannot be a proper subset of itself. And this is also true because the empty set can be a subset of itself. Okay, I'm going to look at the chat box real quick. There was a question in the chat box about, would this most likely be used in statistics more than anything else? It is used in a variety of ways, not just statistics. I can see how it would be used in statistics because you are putting things in sets and grouping things together, and you know that has to do with maybe how you're going to categorize them when you analyze them and describe a population or a sample. But this is used as set theory is actually its own little branch of mathematics as well. So it relates to algebra, for instance, and numbers like the set of integers, the set of counting numbers, the set of irrational numbers. So even just categorizing different types of numbers, also it's using sets. Anytime you put anything in a collection and give it a label, it's a set. So it really is very applicable to a lot of different areas in mathematics and in life in general. You could say this collection of people, this is the set of people that all live in Atlanta, Georgia. That's a set. So it could be used in a lot of different areas. I'm looking at the chat box. I didn't know if there were I didn't see any other questions in the chat box there. Okay, so just wanted to let definitions and symbols relating to sets. I don't know what happened, but I'm back. All of a sudden my audio dropped off. But I just wanted to give you my email address if you wanted to send me an email because you'd like this presentation emailed to you. I have a PDF document with these with what I've done this evening. So feel free to send me an email and just requesting the document from the webinar on sets, and I'll reply back. And I just wanted to mention also, please still read and watch the videos in the chapter about sets. I could not actually cover absolutely everything in this hour dealing with sets. So it's meant to be as a complement to the sets and that type of thing. I appreciate your time. I am so happy that you were able to join us this evening, and I wanted to thank you again for coming. I'm going to go ahead and stop the recording, and like I said, if you have any questions or you want me to send you the presentation, just send me an email at ckhouston1@liberty.edu. Thank you, and God bless.